Hello everyone. In this video, we are going to have an introduction to CCD and CMOS cameras and color filters. Now, I know this is a little bit deeper into image processing, computer vision, but I think when we talked about the camera models, pinhole camera, and different things, it's not a bad idea just briefly talk a little bit about how a camera really works, how it receives these light intensity values, and how it interprets or receives the color. So I just want to have a brief introduction. It doesn't need to be like super technical into electrical engineering, which is not really my background. It's just knowing a little bit about them. And I have 5 different resources: our good textbook on Introduction to Autonomous Mobile Robots, Wikipedia, and 3 other websites. So I use lots of different sources to get you some good pictures. So the first one is the CCD or Charged Coupled Device camera. This is kind of like the most common camera, at least in the past. Now they are being mostly replaced by CMOS cameras, but they are kind of like the most common ingredient in robotic systems, even as of today, because robotics most of the time does not need the cameras to be like extremely intricate, and for some basic task the basic cameras could do a relatively good job. Now, this is not a new technology. It was invented in 1960s in the Bell laboratories, okay? So this is like a picture of a typical CCD camera. So why do we call it charge coupled device? What is it that they do? What's their basic of operation? So it has a bunch of pixels, as you know. Each CCD chip has an array, a bunch of pixels. So you say, for instance, I have 1920 by 1080, right? A HD camera. So it has these many pixels in like X direction, those many pixels in the Y direction, correct? So it typically has, if it's HD, more than, as you can see, about like 2 million pixels or so. And so basically each one of these pixels is a light sensitive element. Okay, how does it operate? Let's take a look. So you can think of each one of these pixels as a capacitor that is being charged or discharged when it is hit by the light, by the photons. In reality, they are not capacitors, each pixel. They are actually photodiodes, as we're going to see later. So it's the photodiode that will accumulate the charge, okay? But you can think of it as like a capacitor that being charged or discharged. The typical size for each one of them is somewhere between 5 to 25 micrometers. So they are very small. That's why several million of them can fit inside the small chip that is like a few mils to a few centimeters. Okay. Now, what's inside of them? Inside of them, you have metal oxide semiconductor or MOS structure. Okay, so again, if you go back and look, what you really have is the semiconductors. Okay, and these semiconductors are basically the basics of the foundations, the structure for collecting the charges. So, how does it work? So when a photon of light hits each pixel, they will free up or liberate the electrons, okay? And then these electrons are going to be captured by some electric fields within each pixel, which we call them potential wells. So here I'm trying to tell you all different terminologies that you might hear when working with CCD or CMOS cameras, so you have some better idea about this terminology. If somebody says, what is potential well or something, at least you have an idea. So the way it is done, I mean, they have a bunch of what we call gates, and on these gates we can apply different voltages. So there could be several gates on each one, and by applying voltages on each one of these gates, we can trap and keep the electrons inside this basically semiconductor layer. So these guys here are those potential wells, right? So these potential wells are these storage areas that can be activated and could be joined together or separated by depending on which one of these gates we are applying a positive voltage, or in terms of electric engineers they say which one is positive biased or something. Okay, so over time, as more photons are hitting the each one of these basically these photodiodes, more electrons are going to be discharged and accumulated over inside these potential wells. And after some time, we're going to see that we're going to freeze this integration. We're going to read those, or basically look at how much charge is accumulated and convert it to some voltage, which we can use for a digital pixel. But right now, so I wanted to show you the notion of gates, the notion of potential well. Now, the number of electrons that is going to be accumulated in each pixel is proportional to the light intensity that is that pixel is exposed to. So, and is proportional. So if I make the light intensity twice as big, then I will have twice as many electrons that are freed. And over time, as I said, they are accumulated. Okay, yes? So that is like the basic, and you can see that as well here. Okay, and again, by applying these different voltages on these gates, we can separate them. We can create what we call a potential barrier between these wells, so they are merged or not merged. Okay? And these are these photons that are hitting these semiconductors and freeing up electrons to accumulate over time. And of course, there is a pixel reset gate, there is a drain voltage gate, there are all sorts of gates that we use for basically creating these wells, separating them, resetting them, which means basically discharging it, drain voltage, and so on and so forth. So there are lots of different gates on a CCD. So if we move on, now, first of all, how would you control how much light is coming through the camera and hitting these photodiodes? Well, one is the iris position. The other one that is more important is the shutter speed. They control the amount of light going through the camera. Especially the shutter speed controls the time that these electrons are accumulated, and that time is called the integration period. Okay? In high-end cameras, the speed of the shutter could be as fast as 1/30,000 seconds, okay, or 30,000 hertz, which is very, very fast, or could be as long as 2 seconds. Then there is this thing called camera gain, which controls the overall amplification of analog signal and conversion. We're going to get to that in a second, but I just want you to know there is such a thing as a camera gain. So what happens after this integration period is done and the CCD has been exposed to the light sufficiently? Then the charges in these potential wells, they have to be frozen, means you don't allow more electrons to get in. Then you have to amplify them because they are not typically large enough charges, and then they have to be read. Okay, so how do you do that? So when you freeze it, you basically don't allow any more electron to be freed, and then you can send them to any amplifying device like a transistor or anything to increase it, like if it is in the term of a current or voltage. And then how do you read? Now the reading is typically performed on a corner of a chip. Okay, so on the corner, if you consider it like a matrix, on one corner of it, you typically start reading these pixels. And typically it's done on the bottom right corner. So at the bottom row, you start reading the pixels one by one for the last row, okay? And then once the last row is done, now you go to the row above it, bring these charges down, and then move them one by one to this bottom right corner and send it here to an amplification device like an op amp, for instance. So because of that, since all of these charges must go across the chip, it is a slow process and it needs special circuit and fabrication to make sure that as these charges go from pixel to pixel, they keep their charges and these transport charges are stable. Okay, so because of that circuitry, first of all, these CCDs are expensive, or at least they were quite a bit expensive, and they are slow. Okay, because that's how you read them. It's just every pixel should be transferred ultimately row by row down and to the bottom right corner to be read pixel by pixel. That is a slow process. Now, is that the only disadvantage that they have? No. Let's look at some of the problems with the CCD. One is these photodiodes that are receiving those or releasing those electrons, they are not sensitive equally to all frequencies. They are relatively sensitive to the visible spectrum, but they are very, very sensitive to the infrared, okay, so to the heat. They are very sensitive, so heat can easily make them release a lot of electron, and then we're going to have the problem of saturation, which I'm going to talk about. But they are very much less sensitive to the ultraviolet. So they are not going to detect blue as well, as good as they are detecting a red side of the spectrum. Okay, so many times your blue channels, they have to be amplified a little bit more than the other channels because these are less sensitive to the ultraviolet range compared to the infrared range. Okay, so that's one of the things. Now, remember I told you that we need to get these signals and these electrons, amplify them and read them. And so there are some parameters in the CCD camera, including the shutter speed, the iris position, and a few other things like the amplification gains and so on, that control the overall amplification of the signal. And then at the end, you have to convert these analog signals to digital by A to D. So there are several parameters that you need to tune to get the response that you want. As I said, the overall camera gain is, or the control for overall amplification of the signal. Now, the problem is what we call inconstancy, because you have a bunch of parameters to be adjusted for each environment and a particular light level. So basically, if these parameters are not exactly adjusted the same each time, you are not going to get the same quality of the image for different settings, okay? And the other one is the dynamic range, which is like the range between your max and min of illumination that you can capture. And that depends on the what we call the well capacity of those pixels. Remember that these electrons are accumulated inside these wells, and so depending on how many electrons they can hold, then that will change the range of the light or luminance that they can capture and display. For instance, if you have a high quality camera, each pixel can hold up to 40,000 electrons. Therefore, you can get a big range of light values or light intensities. But if the well can only hold, I don't know, like 5,000, 4,000, 1,000 electrons, guess what? You cannot have a big dynamic range. So you need to make pixels with bigger well capacities, and that means more expenses. So dynamic range and inconstancy is one thing. Another thing I need to talk about is what happens when this well is all filled. So this well, let's say it has 40 electrons and now it's completely filled, but the light source is very, very bright. And if you want to capture that brightness, guess what? your well is already filled with 40 electrons. It cannot hold anymore. So remember I said that the number of electrons and the light intensity, so if I call this I, and this is the number of electrons or charge of them, Q, this has a linear relationship. So more light intensity means more electrons are freed. But this is only to so much capacity. After that, you cannot hold more. So for instance, this could be like equal to 40 electrons times the charge of one electron, correct? And after that, it is going to what we call saturate. So it's not going to go any further up, and it's going to go flat. Okay, and that linear relation is going to go away. So an object that has so much of light intensity with another object that could have twice as much light intensity could look the same in your image, because the one that is not as bright already saturated the camera, so the second one will definitely saturate the camera. And so above so much of light intensity, all the objects might look alike, okay, because your camera is saturated. But there is even a bigger problem. Not only when these electron wells are filled, they cannot hold anymore. The problem is if there is another pixel right next to this, these guys, when they are filled, they can start leaking into the neighbor pixels, and that is a bigger problem called blooming. So you can see that inside the bright object, you see there is this halo, right? The object is just that smaller circle, but there is this halo around it because the electron wells, or those wells, are already saturated and start leaking into the neighboring pixels. So blooming is also a very, very common problem in CCD cameras. So now, as opposed to the CCD camera and sensors, we have CMOS, CMOS, which is complementary metal oxide semiconductor. So in terms of having pixels and everything, this is similar to the CCD, but remember that in CCD, when you wanted to collect the values and read them, you have to bring them all down row by row and to the one corner to read them off of one basically amplifier, right? But in this case, each pixel has allocated to itself a specific reader and amplifier. So now it can directly read all of these parallels, all of these pixels in parallel, and you don't need to transfer these values. So that does not need a complicated circuit, and that will also be a lot faster. So these CMOS systems are cheaper because they don't need specific circuits for transferring these voltages or charges, and because it doesn't have those, it's not as expensive, and of course it does not consume so much power. So you can see that CMOS chips are using a lot less power, sometimes like 100 times less power compared to a CCD. And for robotic applications where you don't have an infinite source of power, and most of the time your robot is not plugged into the wall running on a battery, this CMOS can be a big advantage because they are not going to drain the battery very fast. Okay, so that's why many of the current systems are using the CMOS technology, which is both cheaper and using a lot less battery. So now to summarize what we talked about, for CCD cameras, the advantages is typically they have high image quality and small noise. They have better light sensitivity, especially if the light is not very bright, it's low light, and uniform pixel response. In CMOS cameras, the advantages is they use a lot less power, they are faster readouts, and so their frame rates are higher, they are more compact and integrated, and they are of course cheaper to manufacture. The disadvantages for CCD cameras is of course they are more expensive, they use more power, they are slower and larger in size. For CMOS, disadvantage is their noise level is higher, although the new ones have made a lot of progress, and so they are now comparable to the CCD, if not better. Their dynamic range is lower in some models. They have rolling shutter effects, which I can talk about that, but I try to skip it. And their pixel to pixel variation is kind of more. As I said, these guys have a more kind of uniform pixel response as opposed to the CMOS. So in general, seems like CCDs are more when you care about the quality of the image, and you don't have too much problem for the power or the cost. And CMOS are the other side, although they are taking over the market and getting CCDs kind of obsolete. So the application for CCD cameras could be scientific imaging like astronomy or microscopy, that you need very, very high quality images. In medical imaging, okay, in cinema cameras, and some specific machine vision applications that need very low noise. But CMOS are used in computer electronics. So your smartphones, your tablets, webcams, they are all CMOS. In car cameras, self-driving cars, in surveillance systems, and in many of the embedded systems and Internet of Things devices, that's the CMOS that is like the leader. One last thing I want to talk about is color. So far we talked about that the electrons are released by the photons hitting on these photodiodes, okay, and that could give you really a single number, a light intensity. But how would you read colors? For instance, if you have an RGB camera or RGB image, how would you read those red, green, and blue? So here you have to use different filters. So filters for green, for red, and blue. And the question is, how would you lay over those filters over your pixels, huh? So in the single chip technology, which is mostly dominated by Bayer color filter array, or just Bayer color, here on every 4 pixels, you are going to lay over 2 greens, 1 blue, and 1 red in the same pattern, and repeat it over and over. So each pixel here will only be covered by one of the filters, either green or red or blue, not all of them at the same time. And you have twice as many green compared to red and blue. Why? Because first of all, the basically luminance of the object is mostly determined by green rather than the other colors, and that's also how our visual system has evolved over time during evolution. Since we humans have seen a lot more green stuff than like red or blue, our eyes are kind of more sensitive to green. I have a video on color spaces, and you can see in that video I talked about these spectrums of red and green and blue, and you see in that one that the green is quite wider than the other ones. So there are 2 greens, 1 red and 1 blue. Now, what's the problem? The problem is now this pixel, let's say, this one right underneath this, that only receives green. But at each pixel, I need to also have red and blue. How do I get those? Correct? So each pixel should have both, all 3 colors, red, green, and blue. But right now, it seems like each pixel will only have 1 color. So how would you get the 2 other components? That's typically done by interpolation techniques, which we call demosaicing. So what is that? So this is how it works. For instance, it says, hey, let's look at one of these pixels a little bit inside. So let's, for instance, look at this one here, right? This one. So at that point, I want to know what is red, what is blue for that pixel. What do? I interpolate. I say, hey, this guy, it has this much blue. This one, it has this much blue. I interpolate between them. That gives me the blue here. And then similarly, this one has so much red. This one has so much red. And again, this one is interpolated between the two. That one has so much red, which is kind of like the average of the two. Okay, and then by this interpolation, whether it's linear or any other, I can estimate the red and blue for that, and similar thing for other ones. So for this blue one, I have to interpolate between these 4 green ones to get the green for it, and these 4 red ones to get the red for it, and so on and so forth. So this simple technique of the mosaicing, which is interpolation, can be used to get those colors. Now, since they are not the actual color of those pixels, they are just interpolated colors, would you get any problem, any artifact? And the answer is yes, you will get some artifacts. Like what? One of the common artifacts that you get is called false color artifact. And that is when you see on some portions of the image, you have some kind of weird colors. I mean, look at this side window, right? Or wing mirror, sorry, not window. I'm sorry, wing mirror of this car. And you can see in this wing mirror, I have a blue portion and a yellow portion. Well, this guy is entirely black. Where are those coming from? I mean, this white part I can see it could be a light reflection or something. But those guys are clearly the artifacts that you could have, and you can see them as well here, that some unrealistic colors would appear. The other artifact is called zippering artifact, and that is when you take the interpolation across an edge instead of along the edge. If you do it along the edge, you're fine, but if you're doing it across the edge, then you see that the shape, the strong, simple edge would kind of looks like a zipper, right? So you see, it's kind of like a zipper, and the quality of the image is completely ruined here, or at least partially ruined. So that is called zippering effect. Some of the edges across which you do interpolation, they lose their sharpness. So that's why in more advanced mosaicing techniques or interpolation techniques, they try to identify the edges and then only interpolate along the edges, not across from them. Okay, so they have to resort to some edge detection as well. And that was the simple chip or simple filter over each pixel technology, Bayer filter. And then there is another one. This is in more advanced cameras, 3-chip technology. Here you split the light that is coming in into 3 separate beams, and each one of them will pass through basically a full blue filter, full green, and full red. And here per each pixel you have one of these filters, so you will get 3 separate channels. Okay, and then you can merge these 3 together. So this way you are not going to lose any resolution, but of course it is definitely more expensive. So hopefully you got an idea, basic understanding of CCD and CMOS cameras and color filters and some of the terminologies related to them. So hopefully they can help you with better understanding of cameras and image processing and computer vision technologies and lectures. Thank you so much, and I'll see you in the next video.